Okay. In this class, we will talk about rate of reactions, in which we will talk about um, general notes that we are concerned about in pharmacokinetic or kinetics in general. And it will be like revision because you know the concept already. So we will talk about rates, and it's just general concepts or revision of whatever you know. Okay, so let's start with, let's say, example of amount A that is changing to amount B. Okay, so this is amount and this is amount of A and B. If we can see from here that this amount is decreasing with time and this amount is increasing with time. So if I want to talk about the rate of decrease in the amount A, if I want to describe it, it will be dA over dt, or the rate of change of the amount A per unit of time. And it will be minus because amount of A is decreasing. Okay? If I want to talk about rate of increase of B, amount B, then I can describe it by dB over dt, or the change, the rate of change in the amount of A over time. And we can just have it in positive sign because amount of B is increasing. Okay, so when we are talking about the order of the reaction, then it's something that or the way that the we have a relationship between the concentration of the drug or the material and the rate of the reaction. Okay, so we are representing the how the drug concentration would affect the rate of the reaction by what we call it the order of the reaction. There's so many orders of so many reactions, but we are most importantly concerned about first order um, and zero order reactions. So first order and zero order reaction, and those what we will talk about in this class. Okay, so let's start with at the beginning. If I want to write the reaction or rate of the reaction of A, let's say, whatever the order of the reaction, it will be dA over dt, and it will be minus because it's decreasing, and it will be K, the constant of the reaction, multiplied to that amount to the power of that order. So N represent the order of the reaction. Okay, so now I will start to talk about zero order, then we will talk about first order starting from this point. Okay, okay, let's start with zero order reaction. Okay, starting off the just the equation we just mentioned, which is to the power of the order, which is zero order. This is called zero order rate constant. This is, we just substitute this with 0 because it's 0 order reaction. This is because it's the amount of A, let's consider it as drug A, is decreasing. Example on that, elimination of A, okay? And we have this as rate of decrease in A. An example on that, let's say it's the elimination rate of A. And this is one of the main examples in kinetic. Okay, so let's continue. If dA over dt equals minus k naught, and this will be, because this will be 1, okay, so it will be multiplied to 1. Okay, so it will be dA over dt, and it's equal minus k naught. Okay, so this is the differential equation of the zero order reaction. Okay, this will be, as I said, the zero order rate constant, and this is the rate of decrease in A. If we want to talk about, we just mentioned this is constant, right? Zero order rate constant. So this is by default, which is the rate of decrease that follows zero order reaction, is constant because it's equal to constant. Okay, the unit of this is mass over time if we are talking about mass of the or the amount of drug A. And accordingly, the constant, which is K naught, will have a unit of mass over time. So this is one important information about zero order constant. The unit would be the same unit of the rate that we are talking about, which is mass over time. Okay, so let's continue with the zero order reaction. Okay, so we have dA over dt that is equal to k naught minus k naught. It's a differential equation, and we need to deal with it to have the parameters that can define the zero order reaction. So we will rearrange it to have similar terms in each side of the equation. So dA equals minus k naught multiplied to dt. Okay, so we have differential equation and we want to deal with that. So we will have what? Integration from 0 to time t, or from a0 to a at time t, integration from 0 to time t. So we will have a from 0 to t equals constant, that will be out, and then from 0 to time t. If we continue the integration, we will have a at time t minus a at time 0 equals minus k naught multiplied to t at time t minus t at time 0, which will be 0. Okay, so at the end, you will have a at time t minus a at time 0 equals minus k naught multiplied to the time, which if we will have a at time t at one side, it will be a naught, right, minus k naught multiplied to the time t. So this would be our zero order reaction equation that represent the zero order reaction, where A as AT is the amount of the drug, in our example, the amount of the drug at time t. A naught is the amount of the drug at the initial time or time equals 0. K naught is the zero order rate constant at time that we are interested in or we are talking about here. Okay, so let's try to graph this equation. Okay, so let's write it again. So we have A at time t equals A naught minus K multiplied to the time, and it's K naught. This is, if you look at this equation, it's a linear equation, okay? And it's similar to y equals m multiplied to the x plus b, or sometimes you will have it as ax plus b. And what we mentioned, we have y, we have x, we have coefficient on x, and we have this constant. We call this, or this would be your slope, and this will be your y-intercept, right? So accordingly, let's go back to our equation here. So if I want to draw a to at the time of t versus time, so I will have y-axis, x-axis. So I have this y, x, and I have it here as t, which is my time, and here as a at certain time, or the amount of the drug at certain time. And this is rectilinear graph. Okay, so let's start with this. According to the equation, I have this as constant, right? And this will be my y-intercept, and this is as the coefficient on x, so this will be my slope, which is negative with a negative sign. So let's, I will give you 1 sec to think about it. We have a constant that is positive, and we have a minus a slope. So our graph will be linear, decreasing, okay? It will be linear, decreasing, and the y-intercept will be equal to a naught, or the initial amount of a, and the slope will be equal to minus k naught, or the zero order rate constant. So I was able to determine by the relationship between the amount of the drug at certain time versus the time that I have, knowing that I have a zero order reaction, I was able to determine the initial amount of the drug from with the graph and the slope, so I can determine from the slope k naught, which is my zero order rate constant. Okay, so we were talking in this equation, or so far we were talking about the amount of the drug. So the equation was a naught minus k naught multiplied to the time, using amounts, amount of the drug at certain time, initial amount of the drug. If we are talking about constant volume that is not changing, okay, so we have amount and we have volume. Can I represent the same or have the same equation by just having concentration terms? Yes. So I may have concentration at certain time equal concentration initial, right? How we did that? You just have, as we mentioned before, concentration equal amount over volume. So you just have to divide the whole equation on the volume, so you will be able, not the whole equation, the amount, sorry, let's correct this. I will rewrite this part. So we have A at certain time equals A node minus K node with time. I need to change the amount to concentration, and we know that the concentration equal amount over volume. If we have constant volume that is not changing, so I'm able to change each amount to its corresponding concentration. So amount at time t over volume will be concentration at time t, and amount initial amount will be initial concentration if I just divide the initial amount over the volume. Okay. So, and the same thing for the graph. Okay, I will just sketch it in a second. So, if we are talking about the graph of concentration at certain time versus time, if we are talking rectilinear and it's zero order reaction, you will know by default, according to whatever I mentioned, that the graph will be like this, and you will have this as your C node or your initial concentration, and the slope will be equal to minus K node or the negative of the zero order reaction. Why is that? Because as I just mentioned that the equation that you have for zero order reaction, but here just in concentration term, it's equal to concentration at certain time equals certain initial concentration minus K naught multiplied to the time. Okay, so the last point that we need to talk about and the zero order reaction is the zero order half-life. What we know about the half-life of the drug in general, the definition of the half-life. We will talk mainly about zero order here, but the definition won't be different whatever the reaction that we are talking about. The half-life is the period of time required for the amount or the concentration of the drug to decrease by 1/2. Okay, so if we are talking about zero order reaction, going back to the equation that we have, A at certain time equal A node minus K node. So by the definition, I want A at certain time to be equal to half of its initial amount, right? And this will happen at the half-life, or sometimes we call it 0.5. Okay, so if you substitute half A node equals A node minus K node multiplied to the half-life, then you can have A node minus A node equal the half-life. Then you can have half minus A node and then over minus K node. So your half-life, if it's following zero order reaction, would be equal to half A node over K node. Okay, so accordingly, you can see that the zero order half-life is proportionally related to the initial amount, and it's reversely or inversely proportional to its zero order rate constant, which means that the half-life, if we are talking about zero order reaction, is not constant, as it's dependent on the initial amount or the zero order reaction. Okay, and I'll stop here to continue about first order and the next video.